Hi, this is Recitation 13. The topic that we are discussing today is definite integrals, but with a focus on Riemann sums. And sigma notation will be in the end, it's just a more practical notation for calculating Riemann sums. So I'm just going to briefly remind you of the context for all of this. So yeah, we've been talking recently about integrals. Definite integral, that means that you have the endpoints of integration like this. It means that this particular symbol here is a number. So what is the geometric meaning of that? If you have a function f that has to be integrable, and usually that means continuous, or it could also be discontinuous as long as it's just a finite number of jump discontinuities. Then, okay, what is the definite integral? It is the net area or signed area. And what does that mean? It's you're going to be looking at the area between the graph of the function and the interval AB on the x-axis. And you consider the areas above the x-axis to be positive and below to be negative. So just a very quick example here. Let's say here's A, here's B, and your function actually looks like this. So what you have here, you have two distinct areas. Maybe let's call them A1 and A2. In this case, the integral between a and b of the function little f is going to be minus a1 plus a2. That's the geometric meaning of a definite integral. Okay, so we also have a physical meaning, the reason why it's useful. Basically, you want to think about it as a total change or accumulated change of something. So suppose you have the numbers a and b, a is less than b as usual. And then you have a couple different interpretations here. When the function represents linear density of something, which is quantity per length, then the signed area, the integral, represents the total amount of that thing. So for example, you could have a line segment where the mass changes, like maybe the left side of this wire is heavier than the right side. So you have a mass function, f of x, a mass density function. And when you integrate that, you get the total amount of mass. If, on the other hand, instead of x, you have a t representing time, and the function f represents velocity, which is length per time, that's a form of the type of functions that we integrate always, just like density, which is per length. If the variable now is time, you're going to have per time. Okay, so if your function is velocity, the integral represents displacement. And then similarly, if your function represents flow rate, once again, here's the important word, rate. That's what tells you this is a per time quantity, just like velocity. So let's say F is the amount of water flowing out of some tank per minute. Then when you integrate that on a certain time interval, what you're gonna get is accumulated change, how much water has flowed out. So yeah, this is the physical interpretation. Well, we're gonna see a quick problem about that. Now here's the thing that we need to remember. The fundamental theorem of calculus, we've covered this already. This is the way that you usually want to compute integrals. It relates it to the concept of an antiderivative. More precisely, if you're able to find a function that's an antiderivative of the one inside of your integral, then to calculate a definite integral, you just calculate that function between the two extremes. You do it on the upper minus on the lower. And that's very simple, very practical. But this is called the theorem. We need to have, before we have a theorem, we need to have an actual definition of what this integral symbol is. Our definition is as the area or signed area. And this is a consequence of the definition. So in practice, even though you almost always want to use this to calculate definite integrals, in practice there are, in theory, there are other ways of computation which are more fundamental. That's what I want to say. When you consider it as an area, It's just a more fundamental concept. So here's just a few examples. Using geometry, if the graph of your function is very simple, it has line segments or pieces of circumference, then you can just use geometry to calculate an area. It is already well defined as an area. We already know like what is the area of a triangle. And in case the graph is a little more complicated than that, then that's the case where you need Riemann sums to calculate it. So the focus for today is going to be on these more elementary ways of calculating integrals. So just keep in mind, you usually never want to do it this way, unless the problem specifically asks you for that, because you have a theorem that tells you how to compute it in a much simpler way. But let's see a few examples of that. So here's a graph. The following graph shows the flow rate of cars in a highway at every instant of time measured in hours. So for example, at 8 a.m., look here, cars were passing at a rate of 3,000 every hour. So yeah, you can see from this highway that around rush hour, there's just more cars passing through it. And then during the middle of the day, it's just a constant flow of 2,000 every hour. So the graph consists of 3 line segments. They're saying that because just by looking at the graph, you might have guessed it, but you don't have confirmation. All right, so now you do have confirmation. It is a simple graph for which you can use simple geometry to calculate areas. The question is, how many cars have passed through this highway between 9 a.m. and 9 p.m.? So take a look at the graph. Time is measured in hours. Technically, when you're talking about 9 p.m., you have to consider it as 21, that the 21st hour is 9 p.m., just so you have a time increasing throughout this time axis. Right, so how do you calculate the total amount of cars? The total change, that is an accumulation. You just have to look at the area below the graph. Let me use this tool here. Area below the graph of this function, which is the flow function. And you're talking specifically between 9 a.m. and 9 p.m. So I'm gonna just indicate here the area corresponding to that interval, area below the graph corresponding to that interval between 9 and 21. And as you can see, it divides nicely into 3 separate pieces that we can compute separately. So how does this work? Total amount of cars. So it is going to be equal to the integral between the 2 time instants of the flow function, f. And what I'm indicating here is that we can break this up into 3 separate areas, 1, 2, and 3, where this is A1, this is A2, this is A3. To calculate those, it's very simple. The trapezoids, A1 and A3, they actually have the same area. Just remember, how do you calculate area of a trapezoid? Let me maybe put that up here. Doesn't matter if it has like a right angle here or not. You're just going to consider the height and the 2 bases, B1, B2. The area of a trapezoid is the sum of the bases, B1 plus B2, times height divided by 2. So this is the kind of figure that we have on the graph. It's just rotated by 90 degrees. The bases are vertical in this case, and the height is this 1 unit. So yeah, what is A1? What is this first area? One of the bases is 2,000. The other one up here is 2,500. The height is 1. So we're going to just do 2,000 plus 2,500 times 1 divided by 2. That's the first area. Second area is much simpler. It's just a rectangle. The base is 10. And the height is 2,000. So 10 times 2,000. And the third trapezoid, if you just look at it, it has exactly the same measures as the first one. So it's going to have the same area, same calculation. So yeah, just figure out what this number is. It's going to be 24,500. That's the amount of cars that went through the highway in this period. Okay, so this is just showcasing the two things that I mentioned. One is that when you want to calculate total amount, total accumulation, and what you have is the flow function, that's the f that we have here, then that's calculated by an integral. So that's one thing. And the other thing is I'm showing you how integrals can be found by simple geometric calculations when the function is simple. You're just calculating areas instead of using the fundamental theorem of calculus. Okay, but what are we trying to do today? We're trying to focus on this idea of Riemann sums, which is a very, not gonna lie, complicated way to calculate it, but it's the most fundamental definition of the integral. So let me remind you briefly about how that goes. If you have an integrable function on an interval AB, a Riemann sum is a sum of the following type. This expression here, where you see that you're summing n little pieces like these, where first of all you have points xi. They go all the way from x0 to xn. So those points, that's called the partition of the interval, they should be like this. They should be an increasing sequence of points that divide your interval AB into several small subintervals. X0 should be the first one, should be A. Xn should be the last point, that should be the other end point of your interval, the B. And then all the others should be inside, not necessarily having the, each interval does not have to have the same measure. In this case, n is equal to 5, as you can see here. That's a partition. And finally, you also have these points xi star. The points xi star should be chosen inside each one of the intervals. So x1 star is some point inside of the first interval. Imagine here's your first interval from x0 to x1. There's going to be a point x1 star somewhere in that interval. And then x2 star is somewhere inside of the next interval. It could be, for example, the right endpoint of that. And so on. You're going to have these points. So yeah, we say a Riemann sum instead of the, because there's many possible ways that you can select all these points. That's what a Riemann sum is. And we've discussed already how each one of these pieces, what it represents geometrically is the area of a very narrow rectangle. Determined by the height of this rectangle is determined by the value of the function. So when you add up all of these areas of rectangles, this is giving you an approximation to the integral. Now we have a couple more pieces of terminology that we already covered. A Riemann sum is called regular when each piece has the same length. So now if we're going to draw a picture, once again, here's A, here's B. Imagine that we're going to divide this into 3 pieces, only 3. So we need x0, x1, x2, x3, but they are all supposed to have the same length this time. That's a partition with 3 subintervals. And the length of each one, we can call that delta x. What is that? Just take the whole b minus a of the whole interval divided by 3. That's what this formula here is saying. So a partition is regular when each piece has the same length, and that length, delta x, is going to be given by this. B minus a divided by the number of intervals, n. And in this case, you have formulas for each one of the points as well. Like the first one, the 0th point, is just a, as always. The next one will be a plus this length, a plus delta x. Next one will be a plus twice that length. And so on up to the last one, which will give you b. Okay, so usually when you're doing calculations, you usually prefer to have a regular partition, regular Riemann sum, because that just the intervals are all of the same length. It's easy to find these sums. So for example, let's look back up here. notice that each piece that you're summing in the Riemann sum, it has this length of the subinterval. x1 minus x0, x2 minus x1, x3 minus x2. Those are the lengths of the subintervals. If it's regular, all of those are going to be the same. They're just going to be your delta x. So when you're calculating this sum, you can factor all of those delta x's. We're going to see that. And then we finally have some names for different types of Riemann sums. I mentioned 3 of them last time, I think during a lecture. I'm going to also mention 2 here now, 2 others. So a Riemann sum is called left Riemann sum when the point that you select inside of each subinterval is the left endpoint of that subinterval. So what this is saying is, imagine that you have your subinterval between xi minus 1 and xi. This could be any one of your subintervals. The point xi star that you're going to select inside here is going to be precisely the left endpoint, which is the xi minus 1. That's what's called the left Riemann sum. Midpoint is when the point that you select is halfway between the 2 endpoints. So now it would be, for midpoint, here's xi minus 1, xi. We can call those like sample points, the xi star. The one being selected is the one right in the middle of the interval. And let's not draw pictures for all these cases, but you get the idea. Right Riemann sum when it's the right endpoint. And now finally, the ones that we haven't mentioned, upper and lower. Upper is when you select it in such a way that the value of the function on that point is the maximum value, the largest value of f on that interval. So just an example, imagine that you have a function that keeps going up and down. And imagine that, okay, here's AB. Inside AB, there's going to be several subintervals. Let's say this is one of them. Here's xi minus 1 and here's xi. So inside of this interval, we're going to be selecting a point xi star. In order to form an upper Riemann sum, what you have to do is select the one that gives you the largest value of the function on that interval. So when you look at the values of the function above this interval between xi minus 1 and xi, the largest value that you find is this one up here. So that's the xi star that you're going to be selecting for that interval. And similarly, a lower Riemann sum would be just select the smallest. Okay, but we can probably move on to the example. Here's an example where we're going to be calculating all those types of Riemann sums. So consider the following function. The interval given, the AB, is this 1 to 8. And the function is x times 6 minus x. Let's try to remember that. Consider also the following partition of the interval into 4 pieces. Here's a partition. 1, 2, 4, 6, and 8. Just keep this in mind. Then the interval between 1 and 8 is being divided into 4 pieces. And it's not regular, as you can see. The first one has length 1. The others all have length 2. So somebody gave you this partition. Calculate the corresponding left, right, midpoint, upper, and lower Riemann sums. And here's the graph of the function, just so you can visualize it. So I circled the points on the partition, and in red you can see the graph of the function. So how do we do this? How do we calculate, for example, right Riemann sum? Right sum. So there's going to be 4 pieces to it. Each piece has, first of all, the length of the interval. So let's say, for example, on this first interval from 1 to 2, the length is 2 minus 1, which is 1. And you're going to do times f of some specific point on that interval. Right sum means that you're going to be selecting the right endpoint of that interval, which is 2 in this case. So I'm going to do this for each one of the other 3 intervals. And I hope you can agree with this. Yeah, remember the partition was 1, 2, 4, 6, 8. So as you can see, 4 pieces being summed. These are 4 areas of rectangles. And now you just calculate this, like 2 minus 1 is 1. What is f of 2? Just go back to the function f and find f of 2. Remember, it was x times 6 minus x. So 2 times 4, which is 8. Yes, right. So you just calculate all of that. The right sum is going to be minus 8. Try to do this just so you can check my math as well, but just to check that you understand. Okay, I'm not gonna give any special symbols for these types of sums. It's fine if you just write the words every time. So we'll do this now for the left sum. What changes? The length of the interval is always there. This part here, 2 minus 1, 4 minus 2, 6 minus 4. That's always there for every Riemann sum. What changes is the sample point that you're selecting inside each interval. In the case of a left sum, you're going to select the left point. So 1 for the interval that goes between 1 and 2. This one. And now for the interval that goes between 2 and 4, you're going to select the point 2. So f of 2 here. All right, this is the only thing that changes. And well, this is going to give you a different answer. I have it here so you can check. This is going to be much larger, 37. In general, if you're doing this with enough intervals, many intervals, you're going to find very similar numbers because every single one of these is an approximation to the integral. And as long as you have enough intervals, that approximation should be good enough. But in this case, because we only have 4 intervals, we're really not capturing much of the how this function is changing. So that explains why the numbers are so different from each other. Okay, but we're just doing this for understanding what the concept is. What is the midpoint sum? What changes now? I'm writing this, and you can tell me if, I mean, you cannot tell me, but you can tell yourself if you agree. Midpoint means that the sample point that you're selecting in each interval is the midpoint of that interval. So in the interval from 1 to 2, that sample point is 1.5. In the interval from 2 to 4, it should be 3. The midpoint, right? So just remember that formula. Those are the two endpoints, xi minus 1, xi. You're going to take the average between them. That's your sample point, xi star. So that's what I did for each one, and I'll once again just go back, plug this into the values of the function. This will be 20.75. Now for upper, we're going to go back to look at the graph. I mean, let me just write this here. The parts that we know are already going to be there. We just need to determine what these sample points will be in each piece. So now let's go back to the graph. Remember that upper means when you look at each piece, you're going to be looking at the highest value of f there and selecting an x where that happens. The most instructive one for us is going to be the second one here, between 2 and 4. On this interval, so we're looking at the values of the function up here. The largest that we can find is f of 3. This one is the largest value of the function on that interval from 2 to 4. So we're going to select the sample point 3 for that interval. Now, similarly, for the first interval, the largest value is at f of 2. So 2 for the first interval, 3 for the second. What about the third one? From 4 to 6 should be 4. Here's the highest value of the function. And then finally, from 6 to 8, you have many negative values for the function. The highest value is f of 6, which is 0. All right, so the sample points will be 2, 3, 4, 6 for each one. You see that the left, right, and midpoint really don't depend on the function. They're always determined by the intervals themselves, whereas upper and lower depend on the values of the function. What do you get when you plug all of this? You get 42. This one is definitely larger than the value of the integral because you're always selecting value, the highest possible value of the function in each sub interval. How does the lower sum work? Let me once again write the skeleton of it. 8 minus 6 f of something. Let's go back to the graph. In each interval, look at the smallest value of the function now. Between 1 and 2, that would be f of 1, which is 5. So we're going to select 1. What about between 2 and 4? There's actually two possibilities this time. It doesn't matter. The smallest f value that we find is 8. It happens at two locations. It happens both at 2 and at 4. So either one of those could be your x star, your sample point, either 2 or 4. So we have 1 for the first, let's say 2 for the second. On the third interval from 4 to 6, smallest value that we find is 0, which is f of 6. And on the last interval, smallest value, f of 8, very way down there. So we are going to select 1, 2, 6, and 8. Calculate all this from the function, minus 11. These are just values of Riemann sums. Once again, they're kind of meaningless because we have so few rectangles, but if you have many, many rectangles, then it starts becoming a good approximation to the integral. So just a remark, an upper Riemann sum is always larger than or equal to the actual value of the integral of the function. So I tried to hint at this right now explaining in this example, but what is the idea? When you're looking at a certain function, you have your interval AB, you have a partition of some type. Let's say this is just one of the sub-intervals of the partition. So if you're calculating an upper Riemann sum, the part corresponding to this interval will have, first of all, the difference, the length of that interval, xi minus 1. This is a sub-index notation, times f of, in this case, it will be xi. What is, when you look on this interval, what is the largest value that you can find for the function? It's up here at f of xi. So what does this represent geometrically? It's the area of the following rectangle. This rectangle, right? It has the base of xi minus 1, and it has this height of f of xi. So when you have your Riemann sum, this piece of it corresponds to the area of this large rectangle here. As you can see, this is larger than the area below the graph of the function on that piece, which would be just this. So the area with an upper sum is always going to be a little bit larger in each piece, and therefore also in the whole sum. So this explains this remark. And similarly, if you have a lower Riemann sum, let's change it like this. If you have also lower, then it's always less than or equal to the integral. But we already mentioned this in lecture. So let's move on to the next example. Here's another problem. The partition given in the previous problem was not regular, as we mentioned, right? The lengths of the subintervals were not all the same. So now let's consider a new regular partition. Let's consider a regular partition. Question, what is the regular partition with 3 pieces? So when you're talking about regular partitions, remember that you have the delta x, b minus a over n. B and a in this case are 8 and 1. N is the number of pieces or sub-intervals, that's the 3. So delta is 7 over 3. And what are the points? The first point is just the A, just the initial point of the interval, 1. And then for every other point, you're just going to be adding this delta x. So 10/3 is the first one, or we can call that second one because the first one is A. The next one, think of it this way. Start from A, which is 1, and add twice the delta x. So in this case, you have 17/3. And then finally, the last one should be the B, if you did your math right. As you can see from here, this does work. It gives you the 8. So what is happening, even though we have these ugly fractions, which can happen, but really all that we are doing here is discovering what are these points that divide the interval into 3 equal pieces. So this is the partition, the x points. Now what they're going to ask in item B is compute the left Riemann sum associated to this partition. So what you have to do, I copied down the function up here so we can remember it, x times 6 minus x. The left sum, let's say, I think the book probably uses this type of notation when the sum is regular, L for left, 3 for the number of pieces, but we can just keep saying left sum. How does that work? Once again, for each one of the sub-intervals, you're going to have the length of that interval, and then times f of some special point, where that point is supposed to be the left end point of that interval. In this case, it's 1, because that's what it means to be a left Riemann sum. So you do this for each one of the pieces. What is the left end point of the second interval? It is this one, 10/3. And plus 8 minus 17/3, f of 17/3. But what is special about regular sum is that each one of these lengths is the same number. If you did your math right, that's what it means for it to be regular. Each one of those is this delta x, which was 7/3. So you can leave that outside multiplying the whole sum when you calculate this. This is going to make your life easier, and I'll just plug in these values into the function. As it turns out, you're going to find 994/27. So just check my math here, but that's the Riemann sum. All right, so usually we will have regular. Now, this is something that I have not mentioned in lecture. This, you can consider this as the actual definition of the integral as area. How do we calculate an integral? If the Riemann sums approximate the integral, and they become better approximations the larger number of intervals that you have, then what you're going to do is just take the number of intervals to infinity. So let's read this formal definition. Let f be integrable. Let's denote by Rn any type of regular Riemann sum. Regular is important here for this definition, with n pieces. So it could be a right, left, upper, lower, or midpoint, or whatever, doesn't matter, but with n pieces. The definite integral, this, by definition, what is that number? It is the limit of Riemann sums when n goes to infinity. The number of pieces goes to infinity. This is the definition that we work with. Technically, it doesn't even need to be regular, although it's just a little bit more complicated to write down. Let's not worry about that. So now, here is using Riemann sums to calculate an integral. So problem, use the limit of right Riemann sums, and I should have said regular right Riemann sums, to compute the exact value of this. By the way, when you look at this integral, we already know how to compute this in several different ways. The function x is just a line segment, the graph of that function, so you can use geometry to find this area. And we also know the fundamental theorem of calculus it's very easy to calculate this integral. I hope you know it by this point. Integral of x is x squared over 2, which you calculate between the numbers 0 and 1. So 1 over 2 minus 0, 1 over 2. That's it. This is the integral. But we're going to try to use Riemann sums to calculate it. And they also gave you this following helpful fact. You may want to use it. There is a formula that tells you what the sum of the first n numbers, n natural numbers, is. And it's equal to this n times n plus 1 over 2. Like, check this, for example, what is this for n equals 4? 1 plus 2 plus 3 plus 4 would be 10. And what happens when you plug in n equals 4 here? 4 times 5 over 2, that is 10. Right? This formula can be proven many different ways. This is just given to you. We're going to need this, and you will see where. So how do we calculate this integral? Using right Riemann sums, regular right Riemann sums, and limits of those. So try to imagine what is going to be our n. Here is the interval between 0 and 1. Here is the function. Suppose that you have our n, the regular right sum, with n pieces. So you have x0, which is just, oh, first of all, let's find the delta x. What is the length of each piece? If there's going to be n of them, the interval is from 0 to 1. Those are the a and the b. N pieces is just some n. We don't know what that is. So delta n is 1 over n. And what are the points? X0 is always the first one. X1 is going to be that plus 1 over n. X2 is going to be the initial plus 2 over n. So on up to, the second to last, xn minus 1. Just follow the pattern. And the last one would be n over n, which is 1. So you have many, many points like this, dividing your interval from 0 to 1. And in each case, you're going to be selecting the sample point, xi star. Yeah, let's do it this way, xi star, because this is a right sum. It's going to be the right endpoint of the interval from, remember the sub-intervals always go from xi minus 1 to xi. And the right endpoint is xi. Okay, so the Riemann sum Rn is going to be, let's look at the first one. The first interval is this one from x0 to x1. So the delta x is 1 over n, is always going to be that. And then you're selecting f of x1. Now, when you look at the second interval, from x1 to x2, once again, the delta x is the same. It's 1 over n, the difference between the two numbers. Because this is regular sum, the delta x's are always 1 over n. And now the sample point chosen in the second interval is x2. Finally, all the way to the last one, f of, here the last interval goes from xn minus 1 to xn. Those are the 2 points. The right endpoint is 1. Okay, so how does this work? First of all, let's put all of these 1 over n's in front of the expression, multiplying the sum of the f's. And remember, the function is just the x function. That's what's inside of the integral. F of x equals x. Let me just scroll back up to the integral quickly so you can see that. Here's f. It's a very simple function. So f of x1 is just x1. F of x2 is just x2. And technically, that 1 here was the same thing as xn. This is the Riemann sum that we have, and we also know what these points are. x1 is 1 over n, x2 is 2 over n, xn is n over n. This is the Riemann sum. And how do we calculate this? 1 over n times, well, all these fractions have a denominator of n, so we can put them together like this. This is the sum all the way up to n, up here. All right. Now this is finally the location where we use the formula they gave us in the problem. They told you a practical way of calculating the sum of the first n natural numbers. And it's n times n plus 1 over 2. So we finally have a workable expression for the Rn, a Riemann sum, which we can simplify now. This is going to be n plus 1 divided by 2n squared. I'm just putting these denominators together and also multiplying by this one. And now we can cancel a factor of n. N plus 1 over 2n. This is the Rn Riemann sum. And now we're almost done. The integral, the thing that we want to find by definition, is supposed to be the limit as this n goes to infinity. The number, if you subdivide into number of intervals going to infinity, so taking more and more sub-intervals, then you're going to find the value of the integral. So we just have now to find a limit as a variable n goes to infinity of this particular fraction. We usually have these limits with the variable x instead of n, but it works exactly the same. How do you think about this limit? Well, it is infinity over infinity, so it's not like you can just plug in to see what happens. You need to simplify something. And we know what to do in this case. I hope both numerator and denominator are expressions of degree 1 in n. So you can divide by n like this. And now 1 over n is going to 0, so you just find 1/2 as your final answer, which, by the way, is the answer that we got before. So what's the point of doing all that? I just want to remind you, what we just did is the actual definition of an integral. It's a process that can be done for any function, although it's very complicated. And it's whenever you prove theorems about integrals, you have to work with this process. This is the definition. This calculation up here, much more practical, much easier, is just a consequence of the definition. It's a theorem, the fundamental theorem of calculus. It is what you want to use basically all the time because it's much easier. But like it cannot, when you're proving theorems about the integral, developing the theory for the first time, what you have to look at is the process below, the definition. So I have a next example here that's going to be very similar. Only thing that changed now, it's the same thing, Riemann sums, right, and also missing the word regular. So now we're trying to find the value of the integral with x squared. By the way, we know how to do this with the fundamental theorem of calculus. X cubed over 3 between 1 and 0 will give you just 1/3. So we already know what to expect for our answer. This is an integral that we could not do by simple geometry this time. I mentioned the previous function, previous area that we were trying to find was the area of a triangle. That area is very easy to find, even if you don't know the fundamental theorem of calculus. This one we don't, because this is a parabola shape. But as it turns out, we're going to find the answer 1/3. And the useful fact that will be needed is the sum this time of the squares. So if you take the first n natural numbers and sum their squares up, turns out this expression gives you that. So we'll see this happening. So, okay, partition. Let's talk about Riemann sums. You have the interval from 0 to 1. 0 is going to be your first point, x0. This is the same partition as the previous problem. x1 is going to be 1 over n. x2 is going to be 2 over n. The second to last point is going to be n minus 1 over n. And the last point will be n over n, which is 1. This is how you partition the interval from 0 to 1 into n equal pieces. Sample points. The points to be selected in each sub-interval. Once again, this is a right Riemann sum. They specifically asked about right. This really doesn't matter when you do the calculation, but they're asking for right. So the first point is between the first 2 points in the partition, you're going to select the right endpoint, 1 over n, and just follow through with this. So what is the Riemann sum? So once again, the delta x is going to be the same, and it can be factored outside of the sum. And what's left inside of the sum is just the sum of the values of the function in each one of the sample points. x1 star, xn star. Delta x is 1 over n, just like before. But this time, the f function is the square function. So when you calculate it on the stars, hxi star is it's I over n. And then when you calculate f on that, you're just raising to square. So this is the Riemann sum with n pieces, and we can try to simplify this now. You have 1 over n times. This numerator is going to have a sum of squares. The denominator is just n squared for each one of these fractions. Now is the time when you can use the expression that they gave you. This sum of squares is always equal to n plus 1, 2n plus 1 over 6. And once again, let's do all of our simplifications. Cut this n with that n, and leave just a denominator of 6n squared. All right, that's Rn. The integral is supposed to be the limit of that as n goes to infinity. So let's try to find this limit now. How does this work? Now, similar to before, when you try to plug in n equals infinity to see what happens, you get infinity over infinity, which is bad. You can try to use L'Hopital, for example, in the variable n, although that's really not needed. This is just a once again, limit of polynomials. It becomes clearer if we expand the numerator. So I'm going to do that now, expanding out this product here. You have 2n squared plus n plus 2n, and then plus 2 divided by 6n squared. So this is a fraction of two polynomials where both of them have degree n squared. So by dividing by n squared, you can really see what the limit does. The 3 over n and the 2 over n squared terms will go to 0. So this leaves you with a 2 over 6, which is 1 over 3. Once again, this is the same answer as before. By the way, Archimedes did this computation in ancient Greece. Essentially the same thing. Of course, he didn't have the limit notation or anything like that, but he did calculate the area below a parabola to be 1/3. That's the area that we're finding here. F of x equals x squared between 1 and 0. This area is equal to 1/3. And what we are doing here is a calculation that uses basic geometric principles, sums of areas of rectangles, and what happens when you take more and more rectangles. All right. So the last thing for today is this so-called sigma notation. I just want to say how this works. Let me go back. When you're doing limits of Riemann sums like this, you're not just calculating one Riemann sum specific with 4 pieces. For example, you're doing it with n pieces. You always have this. This is very annoying to have. Plus, dot, 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 plus. Sigma notation is something that takes care of that. It's just a different way of denoting a similar thing. So technically, the formal definition for that, here's what it is. When you have an expression, let's say e of k, that depends on an integer k, and you want to sum it over all possible values of k between integers n1 and n2, So in other words, you want to find this sum, a bunch of different expressions depending on numbers that go from n1 up to n2. You can do that by, you can denote that by using this symbol here. The letter sigma, this is the uppercase sigma from the Greek alphabet. It has nothing to do with an E. It's not an E. It's like this, sigma. And what you do is you're going to select some variable to be what's called a dummy variable, just like in the integral. You know, when you have an integral, there is a variable inside. That's the variable of integration, this x here, which you can change to anything you want. Similarly, here you're going to have a dummy variable that's being called k here. So you read this like this. The k goes from n1 to n2. And you just put e of k inside of the sigma. So for example, the Riemann sum, this expression here, you see a Riemann sum with a selected number n of points in the partition. It has this dot 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 here because we don't know how many points we're summing. It goes from 1 to n. So you can denote that more compactly by using sigma notation like this. So look at what's happening here. We notice that the things that we are adding are all of the form, there's a number k here, this 2 in this case, and here there's a k minus 1. Like look here, 3, 3, 2, 1, 1, 0. So that's what I wrote here, k, k, k minus 1. And where does k vary? Where does it start and where does it end? It goes from 1 to n. So 1 to n. So this is the same thing as that. It's just a compact notation for the Riemann sum. And other examples, identities that were given in the previous problems. Look at this one. You're summing the number k for k being between 1 and n. So it just represents 1 plus 2 plus 3 all the way up to n. And the problem told us that this is equal to n squared plus n over 2, one of the previous problems from today. The other one is the sum of squares. If you want to represent the sum of the squares between 1 and n, you just sum the k squares between 1 and n. And the problem told you that that's always equal to this. Now there's some very useful, very intuitive properties of sigma notation. Basically, you can split sums and differences inside of it. Should be plus or minus here as well. You can split sums of sums into 2 separate sums. You can factor constants outside. Think about what this represents here. This one, you're summing a bunch of numbers. Each one of them has a c multiplying it. This is like c times e of n1 plus up to c times e of n2. And you know that you can factor a c. Right, so that's just what this property is. It's factoring the c outside of the sum. And then finally, if you add the same constant, so something that does not depend on the k, on the dummy variable, then it's equal to this expression, which is just the constant times the number of terms being summed. If your sum goes from n1 to n2, the number of terms that you have is actually not n1 minus n2. If you think about it, it's n1 minus n2, n2 minus n1 plus 1. That's how many terms you have, and all of them is equal to c. So it's just c times that amount. So those are just some useful properties when you do calculations with sigma notation. Now I'm just going to show you how that works. We're going to do, once again, Riemann sum limit. We want to compute the integral of this particular function, the exact value using Riemann sums. Here are some useful facts about sums of powers. Like this one we already knew, the sums of numbers from 1 to n. And this time, sum of cubes of numbers from 1 to n. By the way, a coincidence, it is just the square of the first part here. This is something that you can check by yourself. It is a coincidence that happens when you do the sum of numbers, let's say 1 plus 2 plus 3. And when you compare that to the sum of cubes, 1 cube plus 2 cube plus 3 cube, the relationship between those two things is that one is the other squared. Just think about this. 1 plus 8 plus 27 is 36, which is the square of 1 plus 2 plus 3, which is 6. So anyway, just a coincidence. We'll think of these two as just formulas that were given to us. And now we want to find the integral. This time it's from 0 to 2. And the function is x cubed minus 4x. So just a little bit more complicated. And we're going to use sigma notation this time, but it is exactly the same procedure that I just showed you. So let's do that. The interval goes from 0 to 2. So delta x this time is going to be 2 over n. If you have n pieces, but now the b is 2, it's not 1. So delta is 2 over n. The points xi, remember I gave you this formula, a plus delta x times I. This is like saying the x3 would be the initial point plus 3 times the delta. So in this case, a is 0, delta x is 2 over n, so 2I over n. Right, this, when you write this, that's the same thing as writing x0 is 0, x1 is 2 over n, x2 is 4 over n, x3 is 6 over n, all the way to the last one, xn will be 2n over n, which is the number 2, the b. All right. So we have the points. The xi star is the same thing as xi, because this is a right sum. Actually, did they say right or left? Yeah, they said right. So xi star is always a point in the interval from xi minus 1 to xi, just like x1 star is in the first interval, which is from x0 to x1. And just say that it's a right sum means that you're selecting the right endpoint. All right, so we have this. What is the Riemann sum Rn? Now we're using sigma notation. You want to add up on all of the intervals the delta x, which is always the same, times f of the selected sample point, which is this xi here. Now delta x, I told you this is always the same number. It's always 2 over n. Here it is actually, 2 over n. It's a number that does not depend on the integration, on the summation variable, the dummy index I. So that number can be brought outside delta x, outside of the sum. And the function f, what is f of xi? F is x cubed minus 4x. So we're going to do xi cubed minus 4 times xi. Okay, so let me just replace the symbols here with what they mean. Delta x is 2 over n. Xi was found to be also 2I over n. This was given above. Okay, so this is what we're trying to compute, to simplify. A sum with an expression involving the summation variable I. Here's I inside. How do we simplify all of this? Well, first of all, let's expand out the expression inside of the sum. You're going to have 2 cubed, which is 8. And 4 times 2 is also 8. So 2 over n. I want to put these into with a common denominator of n cubed. 8i cubed minus 8in squared over n cubed. Why did I do that? Because now, well, the n cubed can be brought outside. It is just a constant, doesn't have I in it. So n fourth outside. If you think about it, there's an 8 that can also be factored and then brought outside. Let me do that. Instead of 2, I'm going to write 16. And what is left really inside? It's a sum involving I cubed and minus n squared times I. How do we calculate this sum? Well, you can split it into two separate sums. The sum of I cubed and the sum of n squared times I, where the n squared can be written outside of the sum. So all of this is using the properties that I just mentioned before, involving sigma notation. All right, now finally we have something to work with. Each one of these, we know what they're going to be. The summation of the numbers from 1 to n is n plus 1 over 2. And this other summation with the cubes is that exact same expression, but squared. Those are the formulas that they gave us above. So this tells you what the Riemann sum Rn is going to be. And n plus 1 over 2 squared minus, there's an n squared outside here. Together with this n, it's going to make an n cube. N plus 1 over 2. Yeah, very good. That's your Rn. The integral of the function given on the interval given is not equal to this, because this is something that depends on the number n of intervals. The integral is the limit of this when n goes to infinity. I'm going to leave this part for you. I'll just give you the answer. It's going to be minus 4. But essentially, you can guess this is going to be a finite number. Just think about what this expression is. Once again, it's polynomial over polynomial. You have a degree 4 in the denominator. And what degree do you have in the numerator? This one is 4. This one is 2 square, also 4. So it does make sense. It's going to be degree 4 over degree 4. It will give you a finite number, which turns out to be minus 4. So I hope you can see that from here. And now also go back to the function and try to calculate this with the fundamental theorem of calculus. Much easier. It will also be minus 4. Do those little checks for yourself. But yes, anyway, this is Riemann sums. Now the topic of Riemann sums is finally complete. I think what's more important for us, I'm going back now, is actually the things that we just did here, this particular example of calculating a specific Riemann sum with just a small number of intervals and different types of them. This is a computation that's easy to do. What we were doing now in the later parts was taking limits of Riemann sums when you have a little n in it. That's usually harder, but it gives you the exact value of the integral. It's important because of that. And finally, the stuff with the sigma notation is just an abbreviation for that procedure.